Hello guys, this is Prime Concept. In this video, I want to look at how the formula known as lens maker's formula can be derived, right? Yes, now what is actually the lens maker's formula? The lens maker's formula is a formula that is used by those that are producing lenses to calculate the focal length of a lens. Now, say you're producing any lens, of course, you need to know the focal length of that lens so that you can inscribe it on the packet for that lens, right? So the formula that these manufacturers use is what we know as the lens maker's formula. Now, in this video, we want to learn how we can derive the lens maker's formula, and then we'll also be learning how to apply it, how to use that to determine the focal length of every lens. Now, you would learn later in this video that the focal length of a lens actually depends on a quantity which is known as refractive index. So it means that if you know the refractive index of a lens, you can actually determine the focal length of that lens. So we'll be learning that in this video. So do well to stick with me till the end of this video so you would understand the concept. Thank you. Now, say we have our lens like this. So this is our lens, and then this is my principal axis, right? Now, if I have a point object, say I have an object at this point, which is O, now, and light from this object hits the surface of my lens, it's going to hit in this way. When it hits, now you would recall that in our lens studies, we mentioned that lens is made of two curved surfaces. So you can see this part is one of the curved surfaces of a lens, and then this is another curved surface of a lens. Now, if light from my object hits the lens, assuming that this other surface is not present, you would expect that when it hits this point, the light would refract and hit somewhere around here, which would form an image, which I would call I prime. Now, but because this second surface is present, the image would not actually be formed here. So this image is only formed here, assuming that this second surface is not present. So then, in an actual case where the second surface is present, like we can see, it means that my image would no longer be formed here. So as a result of refraction from this second surface, it will bring my image somewhere around here. So it means that the actual image will be formed somewhere around there, which I would call what? I. That is the actual image. Now, since I'm moving from air, this surface, into glass, so I'm going to call the refractive index of this first medium, I'm going to call it N1. Then the refractive index inside there, the glass, I'm calling it N2. Refractive index outside there, we'll call it N1 because it's the same as this, right? Yes. Also, since we have two curved surfaces here, I'm going to call the radius of this first surface R1, and then the radius of this second surface, I'm going to call it R2, right? And then also our object, the distance from our object to the center of our lens, we call it U, object distance. Now the distance from this center of your lens to where the actual image is formed, I'm calling it V. Then the distance from the center of my lens to where the virtual image is formed, I'm going to call it, let's say I'm going to call it P. Now, using this, if you recall, in my previous video, we derived a formula known as Gaussian formula, which is used when you have refraction at a single surface. So I'm going to be using that relationship to derive my lens maker's formula, right? Gaussian formula is applied to a single surface. So since I have a single surface here, another single, so I can apply Gaussian relationship twice to these two surfaces, and then I would arrive at my lens maker's formula. Now, considering this first surface, now this is Gaussian formula, N2 over V minus N1 over U equals N2 minus N1 over what? R. This is Gaussian formula, which simply means the refractive index at the second medium divided by the image at the second medium equals what now? Refractive index at the first medium over the object at the first medium. That is what this formula says. Now, so applying this to this first surface, I would have that the refractive index N2 at the second part, which is N2, divided by the image at the second part is actually P. So I'll say divided by P minus N1 divided by the object, which is what? U, is going to give me N2 minus N1 divided by the radius of curvature for my first surface is what? R1. So I'm going to call this equation 1. Now, if I apply the same relationship for the second surface, remember this is refractive index at the second surface. So for the second surface, I'll have N2 over the image, right, at that second surface. Okay, my second surface in this case now is going to be N1 because N2 becomes my first surface when you're considering N2 becomes the refractive index, right, of the first surface if I'm considering this surface now. So N2 is the first, then N1 is the second. So I'm going to say N1 divided by the image at that point. So the image is actually what now? The image is V, the image at that second, the final image is V, then minus N2 now, which is the refraction at the refractive index at the first surface is now N2. So the first divided by what now? We have divided by what now? P. Thank you. Divided by P. So this is going to give N2 minus N1 all divided by R2. So I'm going to call this equation 2. Now, why am I saying N2 minus N1 and not N1 minus N2? I told you that we always take the absolute value. So it means to be consistent, I'll just say N2 minus 1, N2 minus 1 because it will give the same thing since we are interested in the positive quantity for that. Now what I'm going to do is I'm going to add equation 1 and 2. So if I add up these two equations without wasting time, you will clearly see that N2 over P, and this is minus N2 over P, this and this would fizzle out, right? And I'll be left with what now? I'll be left with N1 over V minus N1 over what? U, which would give me what now? To give me, if I add these two, you notice that these numerators are common, so I'll bring them out. N2 minus N1, so it's common, and I would have what now? 1 over, now I omitted something which you should take note of. The radius of my second surface, remember my second surface curves in this direction, so it means that this radius R2 is going to fall into the negative side. So I should use that so that it will be correct. So that when you add these two, you would have 1 over R1, then minus 1 over R2. So this is what you would have. So that if I solve this, I can factorize N1. So I'll have N1 into 1 by V minus 1 by U equals what now? N2 minus N1 into 1 by R1 minus 1 by R2, right? Now what am I going to do? I'm going to divide all through by N1 so I can remove it. So I'll say divided by N1, divided by N1, divided by N1. So if I do this, this can go, right? On this side, I would have 1 by V minus 1 by U. Would give me what now? To give me N2 over N1 minus N1 divided by N1 is 1. So into 1 by R1 minus 1 by R2. So this is what I would have. Now, if you recall, I already told you refractive index. I already explained the difference between relative and absolute refractive index, so that you should know that N2 over N1 is known as the relative refractive index, which I would call N. So if I do that, and also you recall that 1 over V minus 1 over U is equal to 1 over what? F. So if we know these two things, I'm going to substitute. So I'm going to replace this part with 1 over f, because you can see that this is the length formula we learned earlier. So I would say 1 over f equals what now? N2 divided by N1, we have called it N. So I'll say N minus 1, right? Into what now? 1 over R1 minus 1 over R2. So this formula I have been able to derive now. This formula you can see on the board. 1 over F equals N minus 1 into 1 over R1 and then 1 over R2. This is what we know as length maker's formula. Length maker's formula. So it's a very important formula in manufacturing of lenses. So you want to calculate focal length for a particular lens, you would need to know the refractive index. So you can see that focal length of a lens depends on the refractive index of the material that the lens is made from, right? Now, how do we apply this formula? The sign convention. Sign convention. Now for convex lens. So let's do for convex lens first. Now, how do we use this? You should know that for convex lens, your F is positive. Your F is what? Positive. So you want to use this. They tell you a convex lens, right? The first surface is convex, but the overall is convex. Then it means F is going to be what? Positive. So if you're dealing with a convex lens. Now, refractive index does not have convention. It's always a positive quantity. Then, number 2 convention you should note is that R1 is positive for convex surface. Then R2 is what? Negative for concave surface. Right? So it means if I'm dealing with a convex lens, my R1 would always be positive, my R2 would always be what? Negative. Once you're dealing with convex lens, this is how you would use this. So if you're dealing with concave, for concave lens, 1 is that F is what? Negative. Then 2 is that R1 is negative. Then R2 is what? Positive. So this is the sign convention that you would need to be able to apply this formula correctly. So I believe that if you have followed this video up till this point, that the concept is clear to you. So do well to follow this sequentially and then take notes while you are watching this. If this video brings value to you, please don't forget to hit the subscribe button, like this video, comment, and share with 10 of your friends. Tell them this is Prime Concept. Thanks for watching.